Have you ever been watching a movie or playing a video game and just stopped to look at the world, at the clouds or the water or the fire, and just wondered, how in the world did they make that look so real, so alive and chaotic? Well, today we're going to pull back the curtain and see how programmers and artists use pure, cold logic to paint the beautiful randomness of the natural world. Let's dive in.
And that really gets to the heart of the matter, doesn't it? I mean, a computer, at its core, only gets ones and zeros. It's all about strict, predictable rules. So how could a machine like that possibly create something that feels as organic and unpredictable as a rolling ocean or a flickering flame?
Well, it turns out the answer is kind of like a digital magic trick. There's this one core concept, this one secret ingredient that unlocks the ability to simulate all sorts of natural stuff. And once you see it, you start seeing it everywhere.
So let's unpack that secret. We're about to get into the absolute bedrock, the foundational building block that lets a computer fake the beautiful organic randomness we see in nature.
And that secret ingredient is called Perlin noise. Now, the most important word here is pseudo-random. See, true randomness is harsh, it's like TV static. But Perlin noise is smooth, or what programmers call coherent. All that means is that points close to each other in the pattern have similar values. And that one tiny difference is why it ends up looking like clouds, or terrain, or stone, and not just a pixelated mess.
But here's the thing, a single pattern of this noise isn't where the magic happens. The real power, the true artistry, comes when you start layering multiple noise patterns on top of each other. You can think of it like playing a musical chord. One note is fine, but multiple notes together creates something rich and complex. Same idea, but for visuals.
Okay, so let's see how it's done. We start with a base layer, what's sometimes called the first octave. It's a low-frequency pattern, which means it doesn't have a lot of detail. It just gives us the big, broad, rolling shapes. This is our foundation.
Next up, we add another layer, a higher frequency octave. See how this one is way more detailed, more granular? We just layer this right on top of our base to start adding in some of the finer details. And we just keep going. We can keep adding more and more of these octaves, each one with a higher frequency, adding smaller and smaller and smaller details. It's just like a painter starting with a big brush for the main shapes and then moving to a tiny brush for all the fine texture. And then, when you combine all of those simple, kind of boring layers, you get this, a single, complex pattern that looks incredibly natural and organic. We've just turned fuzzy blobs into something that could be the texture for terrain or clouds or even water. It's amazing. Simple rules, layered together, creating beautiful complexity.
Okay, so now we have our tool. Let's put it to work. First up, we're going to look at a scientific application, how researchers use this exact technique to create a physically accurate, totally realistic digital ocean.
So, if you want to make a digital ocean, there are really two main ways to go about it. On one hand, you've got the FFT method. This one is based on real physics, so it's great at simulating things like wind. The problem, as the research points out, it can start to look really repetitive. On the other hand, you have our friend, the Perlin noise method. It creates an amazing random-looking surface, but it's got a huge flaw. It has no idea what wind is.
So what's the big solution? Well, the researchers basically said, why choose? You combine them. You use the physics-based FFT method to get those big, wind-driven waves, and then you sprinkle in Perlin noise, like a digital spice, to break up that repetition and add a final layer of chaotic, realistic detail. And you can literally see the difference right here. On the left, that's the wave height generated by just the physics method. See those repeating diagonal patterns? That's the wind effect, but it looks artificial. Now look at the right. That's the mixed version. The big shapes are still there, but the Perlin noise has been laid on top, roughing up the surface just enough to make it look way more random and natural. It's a game changer.
Okay, so that's the super realistic, scientific approach. But what's absolutely incredible about this tool is how versatile it is. So let's pivot and see how the exact same concept can be used for the total opposite goal, not for realism, but for pure artistic expression, to paint a stylized, cartoony fire.
Creating this fire effect is kind of like following a recipe, and here are the four main ingredients. First, you start with our Perlin noise, but you animate it so it scrolls up. Then you distort it to make it wobble. After that, you use a simple gradient to cut it into a flame shape. And for the grand finale, you apply something called a color ramp to give it that cool, stylized look.
Now, the real secret sauce here is that distortion step. It sounds complicated, but the idea is actually super clever.
You take a second noise texture, and you use its values to mess with the coordinates of your first texture. So instead of pixels moving in a straight line, they follow this wobbly, distorted path. And that's what creates that classic, fluid, fiery motion we all recognize.
The last couple of steps are pure artistry. A simple gradient just carves our wobbly noise into the shape of a flame. Then to get that vibrant color, the artist uses what's called a color ramp. The best way to think about it is like a paint by numbers for light. It tells the computer, for every dark gray pixel, make it red. For every light gray pixel, make it yellow. And that's the key to turning a realistic-looking smoke effect into something sharp, graphic, and cartoony.
And here's just a tiny peek behind the curtain. This is a real line of code from something called a shader. That's the little program that actually creates these effects on your screen. You don't need to be a programmer to get it. This one line is basically telling the computer how to blend all those layers we talked about, the noise, the distortion, the color, to build that final fiery image one single pixel at a time.
And that brings us to the really big idea here. We've just seen one tool, Perlin Noise, used in two completely different ways. One for hardcore scientific simulation, and one for totally stylized art. This is what you could call the coder's canvas, where one simple, elegant idea unlocks an infinite number of creative possibilities. So, what's the big takeaway from all this? Well, it's that Perlin Noise is this foundational tool for faking nature on a computer. It's that digital spice that adds believable chaos to otherwise sterile worlds. And it doesn't matter if you're a scientist simulating an ocean or an artist painting fire, the underlying principle is exactly the same. Layering very simple patterns is the key to generating immense, beautiful, and organic-looking complexity.
It really makes you think, doesn't it? If a pretty simple algorithm from way back in 1985 can be the foundation for faking something as complex as an ocean wave or a flickering flame, what else can be broken down into a set of simple, layered rules? What other parts of our beautiful, chaotic world are just sitting there, waiting for the right lines of code to bring them to life on a digital canvas?